Okay, you guys, now we're going to start talking about larger congruent objects. So we've already talked about what it means to be congruent line segments and what it means to be congruent angles, and we've done a lot of proofs with those, right? Well, now we're going to develop whole 2D figures, right? Polygons that are congruent. So that's the big picture here. And then going along with that, well, what does it mean to be congruent? A big part of that is going to be which parts are corresponding. So which parts lined up, just like we use corresponding with parallel lines. Okay, so here we go. Big picture idea one. Shapes are congruent if and only if, so that's a biconditional, if and only if all of their parts are congruent. So that means every side, every angle, every single thing, but it's sufficient to say that sides and angles. So if every side in order matches every angle, all in the same order in the same corresponding locations. If all the sides and angles are the same, the shapes are congruent, and vice versa. If we find two shapes that are congruent, we know all of their parts match. Okay? Now, order matters is the second idea. Absolutely order matters. So if you say triangle ABC is congruent to triangle DEF, that means A corresponds with D. So I would know angle A. I don't have to even know the picture at all. I know angle first letter is the same as angle first letter of the other triangle. So that always matches with angle D. Similarly, I could pick any two points, right, vertices. I could say side AB, I know is congruent to first letter, second letter. Over here must be DE, right? So I could pick another random one. So like angle third letter must be the same as angle third letter. So C is the same as F, right? So that's what I mean by order matters. A congruent statement is telling you the order of the points, so which ones correspond with which. So this tells me point A in this triangle corresponds with point D in this triangle. So the angle there is the same, the side going off one way is the same, the side going off the other way is the same, so they correspond. Now idea three is these shapes, right, they're the exact same figure, but they've got a different name, so different letters. So instead of ABC, it's called DEF, right? So we renamed it, but it's still the same triangle. And we also gave it a different location and orientation in space. So the three types of ways we could have moved this and kept the triangle the same, right? We didn't bend it, like crumple it up. We didn't enlarge or shrink it. The only things you could do is slide or move it. So you could move it diagonally, down. You could move it anywhere in 3D space. But in general, we consider 2D movement a slide, right? But you could move it in any number of dimensions. But as long as you don't twist it, turn it, shrink it, if you just take the same triangle and just slide it, translate it, move it to the side, it's still the same. So this angle, still exactly the same as this angle. This other angle different, but still the same after the slide, right? Okay, and then we have, well, you could also rotate it too. So when we rotate it, this original angle that you rotate is still the exact same after the rotation. The rotation, if I put my hand on the table and just turn my hand a little bit, it's still the same hand. Any finger length, width, any measurement I want to make about my hand didn't change when I twisted my hand to be pointing forward to pointing sideways. Still the same hand with all the same measurements and like however you want to quantify this hand at any list of values, all those values are the same other than its direction, right? And so same thing, this angle up here has now been rotated and it's this angle over here, but it's still the same value, okay? The other thing we could do is we could flip it like through 3D space. So it's really just a rotation around this pole in 3D space. So it's like you take a playing card or you take your hand on the table, say your palm is face up, and you flip the hand over and now the palm is face down. Or a playing card, you can see the face, it's a jack of diamonds. And then you turn the card over, now you just see the back of the card and it's got a cool, pretty design, but you can't see the jack of diamonds anymore. Still the same card. If I take out a ruler and measure anything and I flip the card, the measurement's still the same, right? So that doesn't change it. And this angle here still is the same as this angle. I could have done sides. I don't know why I didn't do sides, but this side between those two angles is still the same as this side between the two angles. This side over here between the two angles, still the same as this side over here, right? So none of those lengths or values change when you slide it, flip it, or rotate it. And so those are the three different transformations that keep the shape the same. We call those, what do they call it? Isometries or isomorphism, so a change that keeps it the same. All right. So here we go. Let's move forward. So those were the three big pictures, okay? every side and angle must be the same and in the same order because order matters. And there's 3 types of ways we can just move a shape and still keep it with all the same lengths and angle measures. Okay, so let's do this. So 2 figures are congruent if and only if all corresponding parts are congruent. So with triangles, all of the parts we use are, so for triangles, that's 3 sides and 3 angles. That's it. Now, really though, I mentioned over here in purple, it actually, everything's the same. So right, the like length of the angle bisector, if I bisect to this angle here, this length is the same. If I go over to the other triangle and I bisect the angle with 3 arcs, if I bisect that, these 2 lengths are going to match, right? So every single corresponding measurement does match. Now, we're not going to use those to prove it. If we want to prove 2 triangles are congruent, it is sufficient to say all 3 sides match and all 3 angles match and order matters. Okay, so here's 2 congruent triangles. There's 1, 2, 3 things. Now notice this triangle has been like rotated this way. So this angle is now on top. This angle is now on the right. This angle is now on the bottom. I just took this and I can actually do it. We're in the digital world now. Let's actually do the rotation here. So I take this shape and I just twist it over here. I go whoop, and I place it there. And look, the 1 angle, the 3 angle, the 2 angle, the 3 dash, the 2 dash. Now I'm actually enlarging it. That breaks the congruence. I'm just showing you that they line up. But that's what's really happening here. I'm taking this shape and going and lining it up. So all of the corresponding parts match. Okay, so let's go down here. All 3 sides match, all 3 angles match, and in the correct order. And I go ahead and give more examples, so order matters. So let's actually write the congruent statement for that triangle. So looking up at it, triangle ABC. So I choose any order for this first one. I go, I don't know, triangle CBA, triangle BCA. It doesn't matter what order I choose. However, since each letter corresponds with one of the letters in the other triangle, now the order of this second triangle is absolutely dictated by that first. So which one corresponds with A? I go up here, and I go, A had 1 arc, so that's for sure F. So down here, I know that corresponds with F. Then I go up, and B is next. B is the 3 one, that corresponds with E. Okay, so the next one's E, so I'm guessing the last one's D. I'm just going to double check. So C, which has 2 arcs, matches with D, which has 2 arcs, so the last one is D. This order 100% matters, and that's a really common mistake when people are doing problems or writing proofs, is that they jumble the letters. Order absolutely matters. Okay, so from this, we could now list all the things that are matching, not even looking back at the picture. Angle A is the same as angle F. Angle B is the same as angle E. Angle C is the same as angle D, just because C is the 3rd letter, D is the 3rd letter. AB is the same as FE or EF. It doesn't matter which, points you put first. And then BC is the same as ED. Woo! And then AC, 1st, 3rd, is the same as FD. Okay, so we call this rule Cpctc. Now that's an acronym we're going to use a lot, but what it stands for is corresponding parts. So in other words, the parts that correspond with one another of 2 congruent triangles. So if the 2 triangles are congruent, then all of their matching parts are congruent. That's it. It literally just says the matching parts of 2 triangles that are the same. Then all those matching parts are the same, right? So we're going to call it Cpctc. And really, this is just the definition of congruent triangles. Just like we said, for 2 line segments to be the same. Well, literally, line segments have 1 measurement. They're only a 1-dimensional object. The only measurement they have is how long this thing is. If they are the same length, that means every measurement about them is the same. So for 2 line segments to be congruent, all of their matching measurements, aka length, needs to be the same. So that was the definition of congruent segments, and we use that a lot. Definition of congruent triangles just says all 6 matching parts, right? So that's 3 sides and 3 angles must be the same. Then triangles congruent, or the reverse. If triangles are congruent, then the 6 corresponding parts all match, right? And that's 3 sides, 3 angles. Let's just do some problems now, you guys. Okay, so here's an example. So I'm given this congruent statement on top. That tells me everything I need to know. So down here I wrote let's complete the congruent statements first. So DE must be the same as, for second, so that's the same as SP. Okay, GD. So G, that's last letter to first. Remember, because we go counterclockwise or clockwise, these two do form a side. So GD is the same as RS. Okay, angle PQR, so last three letters, is the same as EFG. Right, and then RSP. So R, that's last letter to first second. So last letter to first second, that's GDE. Okay, and we could go to the picture and we could start just like marking this. We could start showing like what is congruent. So I'm going to go ahead and do that. Okay, so we go DE, that's one dash, is the same as SP. Okay, then EF, that's two dashes, is going to be the same as PQ. And now we could just go around the shape. So FG is next. And next would be, just on the picture, RQ, but we'll go up to the top. So FG, RQ, yep. And then the last side is the corresponding side. Whoops, that's four dashes. And 1, 2, 3, 4. And then the angles correspond to it. Like, for example, the angle between 1 and 4 dashes matches the one over here between 1 and 4 dashes. So I would know this is a 102-degree angle because, and I could just use the side markers to tell me, or I could have matched up the letter S with the letter D as the first letter. So whichever way you see that, okay, that's just being flexible and being able to see it in multiple different ways. Okay, let's fill in a few more. So G matches with the last letter R. So R is 84 degrees. Okay, and then we have this 68 for F. Well, F matches with Q, so this is 68 degrees here. Okay, and then 1 dash, this side's 8, and 3 dashes, this side's 12. And I think that's it. Okay, so now let's solve. So it says solve for x and y. Well, I can write two expressions here. I could say, well, I know 6y plus x equals 68. But gosh darn, that's two variables in one equation. There's infinitely many solutions. I could even graph that. Y equals mx plus b. Oh, that's too many solutions. How do we get just one? Well, our other relationship is, and I'm going to do this down here, 2x minus 4 equals 12. So 2x minus 4 equals 12 was our other relationship we got from the picture. So now combining these, I could make a system of equations, okay, two equations with two variables, but really I don't need it because I could just solve this one on the left. So plus 4, we get 2x is 16, we get x is equal to 8, and now I could just plug this in. And now we really just have 6y plus 8 equals 68. Now there's only one solution. So we got 6y equals 60, y equals 10. We could go back and plug it in and just check. So that's 2 times 8, that's 16 minus 4, that is 12. Good. And then y is 10. So this would be 6 times 10, or 60, plus x is 8. So that would be 68. Nice. Checks out. Okay, let's do some more. So, oh, and then also these congruencies are reflexive, transitive, and symmetric. So we won't use the reflexive properties so much with congruent triangles, like in terms of triangle is congruent to triangle. We will use it a lot to say a side of a triangle is congruent to itself, and we'll get to that in the next video. But we will use maybe the transitivity of two triangles. So if two triangles are both congruent to the same, like if they're both congruent to PQR, well, then they're the same as each other because, I mean, they're both the same as PQR, right? But again, order matters. So now let's actually start writing some congruent statement. So here's a picture, okay, that tells us which sides match. So we don't have all the pieces matching yet. We have 3 sides and 2 angles, so we could either use the third angle theorem to say if 2 angles of one triangle, right? If these two match these two, well, then their third angle must be the same. That's one way to do it. Or another way we could have done it is just saying the vertical angle theorem. So vertical angle theorem, these two vertical angles, maybe I'll do it in a different color, like this vertical angle here is the same as this vertical angle here. But now that we have those matching, we could go ahead and write a congruent statement, okay? So let's start with the first triangle. It doesn't matter what letters you use. So I'm going to use triangle, I don't know, ACF. And now we absolutely need to match the order. So 1 arc is D. Okay, 2 arc is C. So C matches with B. And then the last one, the 3 arc, matches with F. So in both triangles, it was in F because they shared that point. Okay, and again, we needed the vertical angle theorem to get that. Okay, So now you're starting to see maybe how we'll do some proofs, right? See how we started with the given, we used the vertical angle theorem, then we proved the triangles were congruent, and the reason there would be really the definition of congruent triangles, or Cpctc. Just that's how you got that the two triangles were congruent. Oh, I wrote the wrong thing. Definition of congruent triangles. Okay, now let's look at this other figure over here. So how could we know these are congruent? Well, first of all, the reflexive property says this side is congruent to itself. So now for both triangles, we know all three sides match. How could we get that that this side is the same as this, or I mean, is the same as an angle? This angle on the left is somehow the same as an angle on the right. Now, we're kind of hand waving here and using something we don't know. No, we can prove it. Whew, I thought we had to hand wave here. Okay, so here we go. Well, to get these angles matched, let's look at it. That's this angle and this angle could match if only the lines were parallel, because those would be alternate interior angles. How could we get those lines are parallel? Well, looky here. We have two lines perpendicular to the same line are parallel to one another. Or more generally, if you don't remember that like kind of special case theorem, you could just use your consecutive interior angle theorem. So because these two angles add up to 180 degrees, well then these two lines again must be parallel. Okay, woo, consecutive interior angle theorem, or two lines perpendicular to the same line. So with those parallel, we do now know that this angle must match this angle. Okay, but we still have, so we have a right angle's the same and this angle's the same. So right angle and this angle. How do we get that third angle? Well, third angle theorem says if two angles match, then the third matches between the two triangles. Or we could do the same thing we did with the other and just say, well, for the same two, either consecutive interior angle theorem, or, and be the converse of, consecutive interior angle theorem, or two lines perpendicular to the third. Either way, we get these lines must be parallel. And so then, if those lines are parallel, just erasing some of these marks here, if those lines are parallel, then that means this angle is the same as this angle, right? So now we got everything matching. Took a little work. You're really starting to see how these are going to become proofs, right? So I can name the first triangle in any way. I'm going to say HJT. That's congruent to, okay, so H in this left triangle was the 2 arc. So that matches with T in this triangle. And then the second letter was J. That was the right angle, so that's K. And then the last one was the pink arc T. And so over here it was the pink arc H. So HJT is congruent to TKH. And that took some work. That would have been a good proof maybe for the next quiz. Okay. What about this? So if triangle WAC, so it tells us those are congruent. Name all the congruent angles and all the congruent sides, okay? Well, the three angles are these three, and they just match in order. And the three segments are this one, and W to Z. So those are the three segments in each. So there's congruent, and then you just match the order. That's it. So there's three angles, and there's three sides. And we just match the order, right? So W is the first letter, so it matches angle S. X is the second, so that's T, and the last one's J. The sides, first, second, so that's ST. Second, third, so that's TJ. And then lastly is SJ, right, for WZ, okay? It didn't say, give a reason, okay. So name the congruent figures. Well, here we'll just use the third angle theorem to get the third angle matches. And then after that, we have all six things. So we could just say triangle, and I'm going to go in order of 1 arc, 2 arc, 3 arc. So that's HCF. Okay, that's congruent. And it didn't matter what order, but now this absolutely matters. So 1, 2, 3, that would be L to J to K. All right, and the next one, let's see what we've got here. We've got all three angles already matching and two of the sides, and then we could just say by the reflexive property of congruence, SV is congruent to itself. So we're done. That's all three sides and all three angles of this left triangle, the same as all three sides and three angles of the other. So I could just make up any letters. This time I'm going to start with the right triangle. So I'll do, this time my order will be using sides. So I'll say I'm going to go across the 1 side, and then the 2 side, and then the 3 side. So I'm going to go triangle STV. I could choose any order, and now I have to choose the other order. So across the 1, then across the 2, then across the 3, that's from S to R, then to V, and then back to S. Okay, about this one. So this one, oh wow, it just literally gives you everything. So across 1, 2, 3, so across 1, 2, 3, we just need to double check between 1 and 2, these angles match. Sometimes they try and trick us. Between 2 and 3, these angles match. Yeah, they just gave us everything. That was a nice, easy one. They didn't trick us. Sometimes they'll put things out of order, and you'll be like, we don't have enough information to prove it, right? And we'll get to that. All right, so let's look at this one. We've got, let's start with the top. So PWZ is my order. So that's congruent to, so P matches with V. I did W second, so W matches with Q. And then I did Z third, so Z matches with S. Right? And then 12, well, let's see. If these two lines are parallel, so here's the transversal and parallel lines, well, then alternate interior angles are congruent. Okay, so that's something. And then if these two lines are parallel, and we have that transversal, well, then we know these two angles are congruent. So we have all three angles match. And we know they share a side. So this side here, by reflexive property, is congruent to itself. However, we don't know this side matches this side, and we don't know that this side matches this side. So I would say not enough information here. We would need some other way to find out that those sides match, because we need all three sides and all three angles match right now. Now in the future videos, our whole plan is, geez, it's hard coming up with 6 congruent things for every triangle. If only there were some shortcuts, like maybe just finding 5 things would be sufficient and we wouldn't need that 6th thing. Oh wait, we have the third angle theorem. So actually, if we just find 3 congruent sides and 2 angles, we already have a shortcut. This third angle theorem says the last angle must be the same. But could we do even less? Could we find like 4 things, 3 things, 2, 1? I don't know. What's the shortest shortcut? Okay. So let's go down here. So determine whether each statement is true or false. Draw an example. So 2 triangles with corresponding congruent angles are congruent. So for 26, that's false. And the biggest problem with 26 is we don't have a single side length. So I'll give you an example. Here's a 60, 60, 60 equilateral triangle with sides of 1. Whoa, that's a 1. And then here's another 60, 60, 60. All of those match, right? Not only like did the corresponding ones match, in fact, all 3 are the exact same and they all match, but this one's of side length 2, 2, 2, right? Or you could have done like a right triangle here, a 3, 4, 5 right triangle, and all those angles are the same as double it, 6, 8, 10. Again, this is all stuff we'll get to when we get to similarity, ratios, proportions, but all the angles, all 3 angles there match, but the side lengths do not. So it's important that you at least have one side length to lock in like the ratio of the 2 shapes. Otherwise, you could have a triangle that's really small and then another triangle with all the same angles but blown up to be as big as a planet. So 26 was false, okay? And then what about 27? So 27 says 2 triangles with angles and sides congruent are congruent. Now, this is actually false because you need to get that the order matches. So for example, let's say we have something of like 2, 3, and 4, or let's not even put numbers, because if we put numbers, we could use trig to actually find all those angles. So let's say we just have a triangle, and we say here's 1, 2, 3 marks, okay, and here's another one with 1, 2, and 3 marks. So all those sides match, they all line up. But then here's the problem. What if we say, okay, so this angle actually corresponds with this angle over here. And this angle in between the 2 and the 3 mark is actually between the 1 and the 2 mark here. And the angles are all jumbled up here. So these 2 are not the same. Now, right now we say this is true. However, when we get to trigonometry, there's a bunch of solving we can do. So actually, sides and angles are inextricably tied together. But let's say for now, because our teacher just said order mattered, let's say false. However, when we get to trigonometry, it'll be a really interesting question to say, actually, are the angle measures dictated by the sides. Like if the three sides matched, is that enough? So I'm going to leave that as like a cliffhanger right now. As of right now, we said order matters. So if the order doesn't match, I would say that's false with the information we have now. However, if we have three sides matching, what does that tell us? So let's leave that as a question, okay? All right, so let's do, I believe we're just doing two last questions here. So 29, we're given some information. Okay, we're given these two triangles. So I'm going to write it. So here's QRS. And then it's congruent to, and I'm going to put it in the same direction, right? So Q matched with G, R matched with H, and J matched with this. Okay, so let's put in what we know now. It says RS is 12, QR is 10, QS is 6, HJ is 2x minus 4. Well, I lined these up, so I know that RS and HJ match without even referring back. We can check it. RS, HJ, they do match. So here's the figure. And it says labeled a congruent diagram. So I'm going to go 1 mark, 2, 3, 1, 2, 3. And I'm going to go in the same order here. 1, 2, 3, and 1, 2, 3. So I labeled all of it. And now I'm just going to solve for those sides that are the same, which is 12 must be the same as 2x minus 4. So then add the 4. We get 16 is equal to 2x. So x is equal to 8. We plug it back in, we get 16 minus 4 is 12. Check. Those sides are the same. Okay, last problem. It's fill in the blank, but I just really wanted to show you a kind of big flowchart proof. We're not going to do many in this section because the very next section is about what shortcuts do we have. And as we start developing those shortcuts, then we start doing a lot of proofs with congruent triangles. And that's kind of the bread and butter of first semester geometry. All right, so let's see. It's not even first semester. I mean, that's really every shape is cut into triangles, right? That's how we investigate four-sided shapes, five-sided shapes, regular polygons with any number of sides. Okay, so we're given a ton of information. So we're given A, B, and C, D. So let's say this is given. All right, I'm actually going to write the reasoning above because there's more room. So this is given. Okay, AD and CB, we are also given that. So I was given. Okay, and AC is the same as CA. Well, actually, that's the same line segment. That's the line segment in between the two triangles. So they're just saying it's the same as itself. So remember, that's the reflexive property of congruence. We're going to use that a lot with congruent triangles. Okay, and then they're given AD and is perpendicular to DC. Well, that was another given. Okay, AB is perpendicular to BC. That was another given. Just going across this top row here first, and then we can separate ourselves from the givens really. So AD parallel BC, that was given. And then AB parallel to CD, that was given. Okay, so now left to right, we already did that top row. Let's see, okay, so if we're in here in the middle, so that being perpendicular tells us that angle D is a right angle. So A to D and D to C are perpendicular, tells us that that's a right angle. Well, that's the very definition of perpendicular lines. Okay, and over here, same thing. This is the definition of perpendicular lines. And then how do we know angle D and angle B are the same? Well, that was a theorem we proved that all right angles are congruent. All right angles congruent. That's one that's used on IXL2. It's a really quick proof, right? You start with a right angle and a right angle, and you just go, oh, well, the definition of a right angle is 90 degrees, 90 degrees, and then you go, oh, well, 90 degrees and 90 degrees are the same, so they're equal, and then you go, oh, and then that means they're congruent by the definition of congruent angle. So it's a quick proof, but we save these steps being right in the middle there by converting it into theorem. So all right angles are congruent, something we're going to use. All right, and then we go over here and we say, okay, well, parallel lines, how do we know angle 1 and angle 4 are the same? So AD is parallel to, so that means this bottom one is parallel to the top, and then we have this transversal going across. So we know angle 4 between the transversal and parallel is the same as transversal and parallel. That's this angle. So that is because the alternate interior angle theorem. And now notice we need totally separate parallel lines to talk about angle 2 and 3, because angle 2 and 3 have nothing to, are created by this side in a transversal. They have nothing to do with this bottom side at all. Okay, so let's clean up this picture a little bit. All right, so now we're going to talk about this second one. So AB and CD. So AB is parallel to CD. and we have this transversal, well then the side created by parallel and transversal is the same as parallel and transversal over here. So that's 2 and 3 are the same. Again, that's the alternate interior angle theorem. Okay, we've almost put it all together. So now, once we have 1, 2, 3 congruent sides and 1, 2, 3 congruent angles, if we say, okay, 3 sides and 3 angles are all the same, then we put it together and the 2 triangles are the same by either Cpctc, or you could say by the definition of congruent triangles. Either one, they're basically the same thing. All right, you guys, what a cool thing. And now the book's using flowchart proofs. Bravo, book. Well done. All right, guys, I'll see you in the next video.